Welcome back. Today we're going to be talking about how to generate sequences using recurrent neural networks. So if you recall what we did last time, we showed how recurrent neural networks can be used to condense or map sequences into vector representations, and those vector representations can then be used for all kinds of predictions, either based on a part of a sentence to predict what comes next, a complete sentence into a vector to predict, say, sentiment, and these vector representations are tailored to be different depending on the task, as the transformation from a sequence to a vector is parameterized and can be optimized for what we want it to do. Today, we're going to be talking more about the decoding problem. If you encode a sentence into a vector, we would like to unravel that vector as a sentence, say, in another language. We will begin by not using the encoding part, just modeling sentences using recurrent neural networks, and then showing how, starting from a vector representation already encoded, you can unravel a sequence. So, here's the outline of what we're going to do. We're going to be considering language modeling, and we're going to start with a very simple sequence model called Markov model. Then we're going to turn those Markov models into neural network models, in this case feed-forward neural network models, and then adding a hidden state and turning them into recurrent neural network models. And finally, we'll just consider briefly an example of unraveling a vector representation, in this case coming from an image to a sequence. Let's look at a sequence modeling problem here. We can take a sentence and try to understand how to generate the symbols or the words in the sentence one word at a time. We can try to understand and predict here what comes after leaves, looking at one step back, what the preceding word was, 2 steps back, and so on, using that history to make a predictions of what comes next. A similar structure or dependencies also appears within a word. If we wish to generate a word character by character, we can take here, try to predict what that character is based on looking at 1, 2, or more characters that precede that symbol. A kth order Markov model is a simple probability model of giving a distribution of what comes next based on looking at k steps backwards. Our task here is to define a probability distribution over sentences. To this end, we need to refine our setup a little bit. We assume that we have a limited vocabulary, capital V, here, so not including all the words in the English language. All the rest of the words that are not in our vocabulary, that are out of vocabulary words, we are introducing an unc symbol as a catch-all. If we see a sentence that has a word that's not in our vocabulary, we just replace that word with an unc symbol and try to predict that sentence. The second thing that we must do is, since we are generating words one at a time by looking at previous words, we introduce a beginning symbol here that's always the same. That is the preceding word for the very first word in the sentence. Finally, we need an end symbol to mark the fact that the sentence should end. So the model has to also predict the end symbol, and once it's predicted, we stop generating sentences. Otherwise, we would just continue generating words based on the preceding ones. So end symbol marks the end of the sentence. A first-order Markov model defines this distribution over sentences, over this expanded set of symbols, by defining a conditional probability of what comes next based on just the preceding word. So now the distribution over, in this case, a 6-word sentence. And notice that the beginning symbol is not part of what we are generating. It is always the same. We write that as a product of probabilities of generating each of the words based on the preceding word. So generating the first word based on that beginning symbol here, all the way to predicting the last word based on what precedes it. And the last word, since the sentence ends, must be the end symbol. So let's take a very concrete example of a first-order Markov model. Here we only have 4 possible words. ML course is an UNC, in addition to the 2 symbols beginning and end. The probability model that the first-order Markov model defines is based on that conditional probability of what comes next based on what the preceding word is. Each row in this table here is identified by the preceding word. So for the first word, that preceding word would be beginning. The row is a set of numbers that sum to 1. It's a probability distribution over what comes next. Notice that none of the preceding words can be the end symbol because we don't generate anything after that. Similarly, beginning symbol never appears as the word that can come next. So we have a table of probabilities where each row sums to 1 and defines the probability of the next word. So let's consider a simple example just to see how to make use of this table. So let's try to understand what the probability would be for a model to generate a sentence. Course is great. The first thing we do is we see an out of vocabulary word. We replace that with an UNC. So actually we are trying to generate a sentence, course is UNC. Then we add a beginning symbol here, as well as the end symbol at the end. So this is the sentence that our model should generate. First thing is to define the probability of predicting course based on that beginning symbol. That probability now is 0.1. Next, we must generate the word is on the basis of the word that precedes it, which is course. The probability of predicting is after seeing course is 0.7 here. Then we must predict the unknown word from the word is. So we are looking at this row and we must predict UNC. The value of that probability is 0.6. And finally, we must predict the end symbol from UNC. We are on this row and we look up the probability of end, the sentence ending after UNC, and that is 0.2. So the probability of this sentence, course is UNC, according to this first order Markov model, is 0.1 times 0.7 times 0.6 times 0.2. Let's look at a simple example of how we would use the Markov model we have just defined in terms of the probability table to generate an actual sentence. The 0th symbol is always the beginning symbol. So then we must look at the row here probability distribution over the first word, what comes after the beginning symbol. To sample from it, we throw a weighted 5-way die, weighted heavily towards ML, a little bit less for course and is, and the end symbol has probability 0, so the sentence cannot end at the very first symbol. So we throw that die. Most likely we would get the word ML, but we might also get the word course. Now the course is the preceding word. We move to this row. We now throw a different weighted die. We might get the most likely outcome here, which is the word is. Then we move to a different row, use a different probability distribution over the next word, throw now a different weighted die. We might get the word unk here, course is unk, and then we move to the row unk, throw a weighted die again, and maybe now we get the end symbol and the sentence ends. This is a way that we can use the first order Markov model, the probability table, to sample an actual sentence that the model implies. In order to use our Markov model, we must estimate it from data. So imagine we have some large corpus, which is a collection of sentences, capital S, and each sentence is of varying length. We already know how to evaluate the probability of a single sentence. So for a particular sentence, small s, we take a product of the probabilities of generating each word in that sentence. So probability of generating the ith word in that sentence on the basis of the preceding word in that sentence. And the product of these probabilities is what the Markov model assigns as the probability of generating this sentence. That's for a single sentence. In order to generate all the sentences in the corpus, we take the probability of generating them independently. We take a product of these probabilities, and this is now the likelihood that our first order Markov model with the specific values in the probability tables assigns to the whole corpus. So we would want to set the values in the probability table in order to maximize this probability. That's called maximum likelihood estimation. It's typically easier to do, as we will see later on, by taking a log so that all the products turn into sums. We will look at later on how to actually solve the maximum likelihood estimation task. But for now, I'm just going to show what the answer is, since it is intuitively clear. To get the answer, we simply count pairs of successive words that occur in the whole corpus across the sentences in that corpus. We say that we have a count, which is just an integer number of how many times pair of successive words W then followed by W prime occurs in the whole corpus. The maximum likelihood estimate of each row in the probability table is simply a normalized version of these counts. So the row corresponding to word W, where W prime here varies, is simply the corresponding count normalized such that across different choices of W prime, the entries in the table sum to 1. So we sum over possible values of the word that can come after W. And this is the maximum likelihood estimate that you could derive as the solution, as the optimizing solution to the previous criteria. Let's now turn our first-order Markov model into a feed-forward neural network model. To this end, we define an input to the feed-forward neural network. It is a one-hot vector corresponding to the previous word. And we introduce an input unit for each of the possible previous words. And since this is a one-hot vector, only one of those coordinate values is 1, the rest are all 0. Let's call this one-hot feature vector x for short. Now we need to now map this input vector into a row of probabilities in that conditional probability table. What is the probability of the next word given that we received this as the previous word? So we'll map this layer of input units into output units, and we have one output unit for each possible word that can come after wi minus 1. Now, the value of each of these output units is then the probability that the word is, say, 1, 2, just the index of the word, index 1, index 2, and so on. So what these output units are trying to model is that the kth output unit is trying to model one probability value in that table, that is, that the probability that the next word is k, given that the previous word is wi minus 1. To perform that calculation, we have the parameter matrix here, w, so the aggregate input to the kth output unit is now, as before, sum over the possible input units, their coordinates, and remember only one xj here is 1, the rest are 0. Values of the parameter matrix from the jth input unit to the kth output unit, plus then potentially an offset parameter w naught k for the kth output unit. Now, these aggregate input values are just real numbers. They are not probabilities. So the transformation, nonlinear transformation we need here is that the pk's are non-zero, and they also must sum to 1 over the possible next words. So we need a nonlinear transformation here of these aggregate inputs that turns them onto a probability scale. A typical transformation for achieving that is something called a softmax transformation. First, we simply exponentiate all the input values, and then we normalize them across the output units. Activation of the kth output unit is exponentiated value of its aggregate input, and then normalized across all the output units that are transformed similarly. So clearly, as a result, these are all positive, and they also sum to 1. So they are valid predictions of probability. This is known as the softmax output layer. All right. Now, did we lose anything by casting the first-order Markov model in terms of the feed-forward model as stated here? No, we didn't, because notice that since only one of the input units is on, then the corresponding output weights, and we have as many of those weights as we have output units, fully control what the resulting probability values are. So, given a previous word, we have still a full control over that row of probabilities for the first-order Markov model. So this is a perfectly valid transformation of a Markov model into a feed-forward neural network model. So you might ask what the advantage is from translating the problem into a feed-forward neural network model. One reason is that these neural network models are quite extendable. For example, previously we had here one input unit per coordinate of the one-hot vector corresponding to the preceding word, as in the first-order Markov model. We can easily add as an input a one-hot vector corresponding to the word before that, and then map both of these into output units that measure the probability of the next word given these two preceding words. So effectively, we are now operating in the space of second-order Markov models. Though, as stated, the approach wouldn't be fully general, wouldn't be able to capture everything that a second-order Markov model can. We can also modify this by inserting hidden layer in between these two in order to look at more complex combinations of the preceding two words in terms of how they mapped to the probability values over the next word. Let's now look at an example of a trigram language model. So we take two preceding words, and for any such combination, we predict a probability of what the next word is. So if we have here the possible words, roughly speaking, then each combination of preceding words, there are the squared of them, and then for each of those combinations, we have to have a probability value of each of the next words. So we will get that times the number of parameters in the trigram model. So roughly the number of words to the power of 3. So in comparison, let's look at how many parameters we have in a simple feed-forward neural network model that takes two preceding words as an input. We have here weight matrix that mediates the input, and the output is of dimension on the order of 2 times the number of words, which is the dimension of the input vector, times the number of output units, since it's fully connected, so 2 times v squared. So we use much less parameters to specify this model. As a result, it is not as general, but it is much more feasible in terms of the number of parameters that we have to estimate. We can make the trigram feed-forward neural network model a little bit more complicated or more expressive by introducing a hidden layer here in between the input and output units and mapping the combination of preceding words to first the hidden layer and then to the output layer. So depending on the number of hidden units that we introduce here, we can increase the complexity of the information that the neural network model can make use of from the pair of preceding words in order to predict what comes next. So the problem with the previous first-order and second-order Markov model formulations, as well as their feed-forward neural network equivalents, is that they look at a fixed history in order to make a prediction of what happens next. We would want this history to be variable, what the model pays attention to, and learnable, so that the model can decide what part of the things that it has already seen it should pay attention to in order to decide what comes next. So let's look at how we can translate this language modeling problem into a recurrent neural network problem. So to that end, we feed in to the model a one-hot vector of the previous word, where t now refers to the time or position in the sentence when we are making a prediction. So we are trying to predict wt, what the next word is. We feed as an input wt minus 1, one-hot vector of that. we will denote this input as a vector xt. So at time t, we have a vector input xt. And the length of that vector is simply the number of words that can precede. We map this into a hidden state. Let's say there are m hidden units, and call the vector of activations of those hidden units st. So st is a vector, m-dimensional vector of activations of the hidden units. And we say that the parameter matrix that mediates this interaction is now WSX. Once we have the hidden state activations, we map those into output unit activations that are now the probabilities of the next word that we wish to predict. And we use parameters here, WO, to perform that transformation. So as a result, we get a vector of values where each coordinate of this vector PT is the value of the output unit. So the probability of a particular word that would come next at time t. All right, so as stated so far, this is just a feed-forward neural network with a one hidden layer. We make this into a recurrent neural network model by feeding in the previous hidden state activation. So we introduce here as an input also the vector st-1. So what we knew previously, what we had computed previously, we feed it also as an input. And there's another parameter matrix that now mediates how that previous state is mapped as an input to the hidden state, and call that WSS as a matrix. All right, so effectively we've created this loop here where the information that we compute at the current time step in terms of the activations of the hidden units are fed as an input at the next time point. So let's see how this model can actually look further and further into the preceding history. So clearly the state that we have at time t is the only information that we make a prediction about the next word. So let's look at what's in that state description. Clearly the one-hot vector representation of the preceding word is affecting that state. But also the preceding state is affecting how that hidden state activations are calculated. Now, the previous hidden state was calculated on the basis of the word 2 steps behind. So that information is also in ST. Similarly, ST-1 is affected by the word 2 steps behind. And it also depends on ST-2 that's affected by word 3 steps behind, and so on. So ST carries information from the beginning of the sentence. The whole process is started with a one-hot vector representation of that beginning symbol, as well as a state vector, which is just all zeros. So let's compare what we have here to the recurrent neural network encoder that we considered previously in the previous lecture. So here we have an input xt that we will map to a hidden state activation, a vector st, that is then mapped to an output distribution over the next word, so a vector pt, probability vector for what the next word will be. In calculating the hidden state st, we also feed in the previous state as an input, st-1. And so we have this loop as discussed. So the previous state comes in as an input into the calculation of the next state. So here we have the encoder RNN state update of the basic RNN model. We have an input vector transformed with a weight matrix into an input to the state calculation. We also take the previous state, transform that, take a nonlinear transformation, and as a result we get now the updated state vector, which is now the activation of these hidden state units. Now this process continues from the beginning of the sentence as we feed more words into the model, and it is performing the same function as the encoder. Now in addition, we derive from the state at each time point also an output distribution. So we take the state vector, we transform it via the softmax transformation into an output distribution of what happens next. So the only difference really here is this one, that we use the current state of the encoding process along the sequence to derive the distribution over what happens next. We can represent our RNN in terms of the boxes as we've talked about before. Now we take a previous state, the input, transform that into a new state, but then also derive from the state that we just calculated a probability distribution over the next possible words. So the only difference here is really this addition of how to derive the probability distribution over the next word from the current state. Other than that, it is the same type of box as the RNN used to encode the sentence. As it should, since the RNN really needs to encode the history of what has been generated so far in order to understand what should be generated next. A similar difference here in the much more complicated LSTM architecture is that the encoding process is exactly analogous, and we just add an output distribution that's derived from the current state. So how do we use these RNN models now to translate a vector into a sentence rather than just generating a sentence from scratch? The only difference really is the initial state. So previously we didn't have any initial state. It was all zeros. We get a null word or the beginning symbol. We create a distribution over the first word. We sample that word. That word then becomes as an input to the next transformation, as well as the state that we updated and so on. So we can sequentially sample a sentence until we create the end symbol, just as in the Markov model case. Now, when we are starting from a vector, we simply use the vector itself as the starting state, rather than all zero vector. As a result, each of the sequential transformations of the RNN architecture, subtracting what it has already generated in terms of the sampled words, gauging what's left to generate, and proceeding until the end symbol arrives. We don't just have to take a vector from a sentence and translate it into another sentence. We can take a vector representation of an image that we have learned or are learning in the same process and translate that into a sentence. So go from one modality to another. Here's an example from a paper that they took an image, translated into a vector using a complicated convolutional neural network architecture. You get a vector that is now the initial state of the LSTM architecture, and then you unravel with the LSTM to predict corresponding sentence to that image. This architecture is then trained from a pairs of image and image caption, and here is just an illustration of the type of things that it can generate. So some things are generated without an error. Here is an image, and what the model predicts corresponding to this image is a person riding a motorcycle on a dirt road. So very accurate. And it makes also some errors. The thing to understand here is really that since these are very complicated models, they can also memorize the examples quite well. So in order to understand how well they actually do, you would have to compare these sentences to the sentences that were available during training. So it's not just picking a nearest neighbor of those sentences to associate with the image. So, key things to understand from this lecture. are Markov models, what they are, how we formulate them, how we estimate them, how we can sample from them, how we can translate a Markov model into a feed-forward neural network, how we can turn that feed-forward neural network into a recurrent neural network, and thereby unravel a sentence using evolving state from the RNN, at each point predicting what the next word is. And once we have this architecture that can generate sequences, such as sentences, we can start any vector coming from a sentence, image, or other context and unravel it as a sequence, as a natural language sentence.